Well, here we are in podcast number 7, where we're going to focus our attention a little bit more specifically on the effect that temperature has on our rates of our reactions themselves, right? How does an increase or a decrease in our temperature affect the rates of our reactions, and why does it affect those? So reaction rates usually increase as we increase the temperature. And now this is not true for every single reaction, but for our purposes, it's like 99.99% true, and so we might as well just call that good, all right? If we increase the temperature, our rate is going to increase. And it says every 10 degrees Celsius increase. This is not a hard, fast rule. This is a very generic rule, but in general, somewhere around every 10-degree temperature increase, then we're going to double our reaction rate. And my figure here just kind of shows that, right? We've got some glow sticks, and we've got some glow sticks inside and outside of ice there in part A. And notice that inside, they're not glowing quite as brightly as the ones that are outside at room temperature. And over there in figure B, right, when we stick the glow sticks into a warmer bath of water versus what would be outside, they are glowing brighter than the ones that are outside. So as we increase the temperature, the reaction that's taking place inside of those glow sticks so that they shine is happening faster, and we see that as the brighter light. If we go back to somewhere around chapter 5 in the book, we learned about gas laws. We learned that, right, the gases are moving at a temperature, and that temperature gives us the average speed of a molecule. We could also calculate the kinetic energy of molecules because that is based on not only how fast they're moving, but also how massive they are. Right? Those two things lead us to kinetic energies of our gas molecules. And so at higher temperatures, our gas molecules are moving faster, thus they have a higher kinetic energy. Right? Just like if you're thinking about a car moving 5 miles an hour versus a car moving 100 miles an hour, you'd rather get hit by the one moving 5 miles an hour than 100 miles an hour, right? Because that's moving faster, has got more kinetic energy. That's the same thing as with a higher temperature. Right? As we increase the temperature, more and more of our gas molecules are moving at a faster speed. All right, now as we increase the temperature then, and we're increasing the speed, then we're also increasing the average kinetic energy, which means that the likelihood of us having collisions with enough energy to overcome the activation energy is greater, thus we have more effective collisions take place. So let's say that we had to have our gas, if our oxygen molecules were moving at least, say, 800 meters per second, then they would have enough energy, right, enough kinetic energy to overcome the activation energy to have an effective collision, have the reaction take place. Well, if our gas was at room temperature, right, only the molecules up in here would be moving fast enough in order for us to have effective collisions. If we increase the temperature, though, up to, say, 1,000 degrees Celsius, right now, all of these oxygen molecules are going to be moving fast enough and have enough energy in order for us to have an effective collision. So you're going to have a lot more effective collisions, and so your rate is going to increase because we increase the temperature. Well, as we've been going through this chapter, you might have been asking yourself where this rate constant comes from. All right, we've just been using it as some constant that is effective for one specific reaction. Well, there is a way of calculating that rate constant. And so we show that the rate constant is equal to P times this thing we call Z times F. Okay, P is our steric factor. All right, and so what this means is that depends on the molecules, right? So the more likely we are to have collisions with the right sterics, the larger that p-value is going to be. If it's really complicated to have them be exactly aligned, then you're going to have a smaller steric factor, a smaller p-value in there. Our z's are how often we have collisions. right? And so the collision frequency is going to be related to, well, how much the concentration is of our reactants, and it's also going to be related to the temperature, right? The faster they're moving, the more likely there are to be collisions, or the more frequent the collisions are going to occur. And then lastly, our F is the fraction of those collisions in which we have enough energy to overcome the activation energy. If you can't overcome the activation energy, it doesn't do us any good. We're not going to have a reaction take place. The more of those we have, then the higher our rate constant is going to be, the higher the rate of our reaction will be as well. All right, so this is one of those equations. Not going to use the equation. However, we want to understand what it means. Meaning, right, understand that, right, the more likely we are to have the right sterics, the higher our rate constant is going to be. The more frequent we have collisions, the higher our rate constant is going to be. The more collisions that have enough energy, the higher our rate constant is going to be. All of those are going to affect our overall rate of reaction. We could go in and do even more fancy stuff by saying, okay, that F factor from the previous equation is equal to E to the negative activation energy over RT, and calculate all these things and plug it back in. Right, plugging this back in here for our F. Right, we're not going to do any of these calculations. Right? I just want you to see that there are ways that we can calculate each one of these steps that gets us to that rate constant overall. It's not just some value that's out there. It's something that we have to calculate for every specific reaction. We luckily are not going to calculate. Right, well, now we're going to turn our attention to something that we call the Arrhenius theory. All right, and so the Arrhenius theory, kind of dates back to some of the information that we learned again back in chapter 5, which was our gas law chapter. And we probably, once we see this in play, have worked problems using a very similar equation in Chem 1. So the Arrhenius equation is rearranged here to show that we can plot it as a line. For some reason, we as chemists love to plot things as lines. But notice that, right, again, we have y is equal to ms plus b. Right, and so what we get here is that we can plot, right, the natural log of k on our y-axis, that's the axis that goes up and down, versus 1 over t on our x-axis, that's the axis that goes along our horizon. And we can find then that the slope of our line is equal to EA over our R value. This is probably the only thing that's on here that might hop up on any equations or something like that, or sorry, any homework problems or anything like that, is that there's a relationship between our activation energy and R and the slope of this line. All right, but what we really want to do with this equation, right now, this equation, what we really want to do is we want to say, okay, well, what were to happen if I were to look at this line and I were to plot things at 2 different temperatures? All right, could we then use this to solve for our activation energy? Because that's going to be important, right? If we know how big or how small that activation energy is, then we know how easy it is to overcome it. Small activation energy, easy to overcome. Really big activation energy, much harder to overcome. When we plot those things as a linear plot, and then we relate the equilibria constants and their temperatures at 2 different points, what we get is something that's called the Clausius-Clapeyron equation. Right here, we are relating, right, those equilibria constants and temperatures. To get the activation energy, we probably saw something similar to this equation where we did pressures were related to our enthalpy change over R times 1 over T1 minus 1 over T2 in Chem 1. Right, this is an extension upon that. Here, though, we're more interested in looking at our rate constants and how that changes this activation energy. And so what we want to do is then use this Clausius-Clapeyron equation in order to solve some problems. So let's see that played out. Here we've got a sample problem using that Arrhenius equation. It says our rate constants for a reaction. Oh, it's nitrogen dioxide plus carbon monoxide producing nitrogen monoxide and carbon dioxide. Okay, we have some rate constants there at different temperatures. It says what is the value of the activation energy in kilojoules per mole? All right, so what we need to know is just stay consistent with K1, T1, and K2, T2. All right, whatever you want to call a K1 or K2, that's cool, but just make sure that the temperature that goes along with your K1 is going to be called T1, and so on. So we have our Clausius-Clapeyron equation. Right, so we're going to write that out. All right, and so it does not matter which one you're going to call, K1 or K2. I like to have the larger K value be K2 if I can, if I get a choice in the matter. So I'm going to do that. I'm going to say, okay, this is 23.0. And K1 then has to be the other one, which was 1.3. That is equal to our activation energy. We're looking for that. We're looking for that in kilojoules per mole. So I'm going to put my R in kilojoules, 8.3145 times 10 to the minus third kilojoules per mole Kelvin. Remember, that is this gas law constant is not the gas law constant for PV equals nRT. All right, now 1 over. All right, temperature 1. Well, I called K1 1.3, so temperature 1 has to be 700 Kelvin. 1 over temperature 2, which thus must be 800 Kelvin. All right, now we're going to work through all of this, right? Got a lot of like little algebra and stuff in there, so make sure that you can get the same answer that I get here. If you don't get this, keep working it back through and make sure that you can do these, because you will do these on exams. We're going to get this to be 134 kilojoules per mole for our activation energy. All right, we're going to continue this problem on our next slide by looking at it in a little bit of a different way. All right, so again, we have the exact same information, but here it wants us to calculate what is the rate constant at 750 Kelvin. All right, well, we found the activation energy in part A. All right, now you can use any pieces of data that you want from here. Right? It does not matter. I'm just going to use these two pieces. You could use the 23 and the 800 Kelvin. It doesn't matter, right? But you just have to stay consistent. Once you pick one of them, you have to use that through the rest of it. So I'm just going to use my Clausius-Clapeyron equation. So we've got, all right, the natural log. Okay, now, right, it doesn't matter which one I'm going to call K2 or K1, but I want K2 to be bigger. And I know that K2 should increase as the temperature increases. So I'm going to call K2 being the one that I don't know. And then the one that I do know is the 1.3 inverse molar inverse seconds. All right, now we've got our activation energy, all right, and that we found in the first part of our problem was 134 kilojoules per mole. divided by, all right, now our gas constant, 8.3145 times 10 to the minus third kilojoules per mole Kelvin, times, all right, 1 over temperature 1. Well, I called K1 1.3, so the temperature that goes along with that is 700 Kelvin. And minus 1 over T2, in this case, it is going to be the 750 Kelvin, because that is the temperature that goes with K2. Right, again, there's a lot of algebra that has to go in here. And remember, right, that this is the natural log of K2 minus the natural log of what was on the bottom there. All right, well, anyway, we should be able to work through this. And you should get that K2 for this is going to be 6.0 inverse molar inverse second. Make sure, again, that you can get the same answer that I get working through those. All right, one more sample problem in this chapter. Well, we know here in this sample problem that we have ethyl acetate is going to react with OH, right? It's in a basic solution to produce acetate and the C2H5OH. Okay, so we have this reaction. It says that the rate of this reaction increases by a factor of 6.37 when we increase the temperature from 15 degrees Celsius to 45 degrees Celsius. We want to calculate our activation energy. So this is similar to part A of the last problem. However, we have a couple of new factors in here. Number 1, temperature must be in Kelvin. Don't forget that. So let's convert our temperatures into Kelvin. So we have 288 Kelvin and 318 Kelvin. All right, next off, we're going to do the natural log of K2 over K1. I don't quite know that yet. I'm going to leave it like that for right now. We're going to look for our activation energy, and it's going to be in kilojoules per mole, so our R is 8.3145 times 10 to the minus third kilojoules per mole Kelvin. All right, times. All right, 1 over T1 minus 1 over T2. All right, well, I'm going to call my smaller temperature T1. So 1 over 288 minus 1 over 318. So what are my K2 and my K1? I know that the rate of this reaction increases by a factor of 6.37. So what if I called K1 1? Okay, well, if the rate increased by a factor of 6.37, then K2 has to be 6.37 times greater than 1, which is 6.37. All right, now we've got everything in place to just calculate our activation energy. And when we do so, we're going to get that our activation energy is going to be 47 kilojoules. So again, make sure that you can go back and get that same answer. All right, that ends another podcast. Next, we'll be working on podcast 8, which is where we're going to talk about things that are called reaction mechanisms and how those affect our rates of reactions. And that's the last one in this chapter.